If you ask a man who lives along this beach in California what a beach is made of, he'll probably say light-colored sand. However, this beach in Hawaii is made of small grains of black volcanic rock. This beach at La Jolla, California, is made of pebbles and cobbles. In southern Florida, the beaches are composed mostly of small bits of seashells. And some English beaches are made up of small, flat rock fragments called shingles. Actually, beaches are composed of whatever loose material is available. People say this California beach is made of light-colored sand. But what is the sand composed of? Tiny grains of quartz and feldspar, the two most common minerals found in solid rock. Where could the billions of grains of minerals that make up this beach have come from? And how did they get here? All along this coast there are streams that flow down to the beaches. And when a stream is dry, we can see that its bed is actually a trail of sand. If we go up one of these trails, we should be able to see where the sand comes from. Up in the mountains, we come to a place where the stream flows over solid rock. Here, because of rain, heat, cold, and chemical change over thousands of years, the solid rock breaks down into bits of quartz, feldspar, and other minerals. Soon, the rock debris is washed into a stream and is on its way to the ocean. By the time the rock debris has reached the coast, it has been refined and sorted out. The bigger, heavier chunks of rock have been left upstream. The smallest particles have been washed out to sea. What is left are hard, durable grains of quartz and feldspar, the typical raw materials of a sand beach. Now let's find out something about how beaches are formed. Anyone who has built a sand castle below the high tide line knows something about the processes that shape beaches. The waves have restored the beach to its original condition. When a wave washes up on the beach, sand grains are lifted up by the water. Each wave picks up millions of sand grains and moves them. What effects do these movements have on the beach over long periods of time? Still photographs of this beach have been taken from the same camera position over a period of years. Let's compare some of these photographs. The sand comes and goes according to the season. At the end of a summer, the beach is piled high. At the end of a winter, the sand is gone. The following summer, the sand returns. But why? In summer, the waves that wash up on this beach are small and carry less energy than the winter waves, which are bigger and more powerful. Such seasonal changes in wave size may be the cause of the seasonal changes in the beach. Let's check this idea. This is a model beach in a wave tank. We'll be able to make waves of different kinds in the tank and see what effect they have on the beach. First, we'll make some small waves, the kind that are most common in summer. To speed up the process, we'll use the time-lapse camera and condense 2 hours into 30 seconds. The small summer waves push the sand toward the shore in the form of migrating sandbars. Eventually, the waves push enough sand onshore to form a steep beach face. Now watch what happens when we make bigger waves, the kind that strike the beach in winter. The bigger winter waves gouge out sand from the steep slope and deposit it as sandbars offshore. The result is a beach face that looks like this. Now watch what happens when we make summer waves again. The sand that was taken away from the slope by the big waves is put back again by the smaller waves. In other words, the sand moves back and forth between the exposed beach face and the underwater part of the beach slope. If sand moves only on and off shore with the seasons, why doesn't it pile up at the mouths of the rivers that deliver it? Why does it form into beaches that stretch for hundreds of miles down the coast? You may have noticed that waves usually approach the coast at an angle, not straight on. The reason for this is that most waves are created by storm winds blowing far out at sea. If a storm occurred any place except here, say in one of these areas, then the waves created by the storm and traveling out from the storm area would approach the beach at an angle, not straight on, regardless of which way the beach is facing. Today, the waves are coming in from the northwest. Notice what happens to the waves when they enter the shallow coastal waters. They bend and tend to become parallel to the shoreline. But as you can see, the bending is not always complete. The waves pass through the surf zone at an angle and strike the beach face at an angle. Let's find out what effect waves like these have on a beach. First, let's find out what happens to the sand on the beach face, the exposed part of the slope. These red markers will show how the water moves. Let's watch the red markers again, this time tracing their movement along the beach face. The sand grains on the beach face must be following a similar path. What's happening to the sand on the part of the beach slope that's under deeper water in the surf zone? The waves passing overhead move the sand back and forth toward the shore and away from the shore. But are these the only directions in which the water is moving? Watch. The dye shows that the water is moving down the coast as well. Now we'll repeat the experiment, this time putting another spot of dye just outside the breaking waves. The second spot of dye shows that the water outside the breaking waves hardly moves at all, while the dye within the surf zone moves rapidly down coast. When the waves enter the surf zone, they break at an angle and cause this down coast flow of water called a longshore current. Now let's see what this current does to the sand in the surf zone. The sand being moved onshore and offshore by the waves is also being moved down coast to the left by the longshore current. From the air, the pattern is clear. The waves approach the shore at an angle. Even though they bend somewhat, they strike the beach face at an angle. The sand on the beach face is carried in a series of arcs down the coast. In the surf zone, the sand grains are being moved not only back and forth, but also down the coast by the longshore current. Such movement of sand on the beach face and in the surf zone is called longshore transport. So we can think of the beach as a river of sand. The beach face is one bank of the river, the outer edge of the surf zone is the other. Much more sand is moved in the surf zone than along the beach face. These groins, built along a nearby beach, provide further proof of longshore transport. The sand has piled up on the same side of each barrier, thus showing the direction in which the sand is moving. Measurements of such accumulations of sand along both coasts of the United States show that the sand moves southward in most places most of the time. These figures show the number of cubic yards of sand that move south each year by these locations. Let's take a closer look at one of these places. We know the sand is moving down coast along this beach toward the harbor at Santa Barbara. Why does the beach appear to end here? And why has a sand spit over 300 yards long formed off the end of the breakwater? We can answer these questions by observing a model of the harbor in a wave tank. The waves strike the breakwater at an angle and bend around its end into the harbor. Now we'll add some sand and create a beach. Longshore transport carries the sand along the shore. The breakwater, acting as a dam, stops the sand, but only temporarily. When the sand reaches the end of the breakwater, the incoming waves carry the sand into the harbor. Once inside, the sand settles out in the quiet water behind the breakwater, and a spit is formed. Now we know that the sand flows underwater along the outside of the breakwater and feeds the spit. Let's watch this process once again.